So this week I'm very pleased to introduce Chris Rodell. So several people asked, recently there was this big heat thing and they heard about the heat dome on the news and stuff, and people were saying, hey, I really can't tell what's the science here, what's just stuff being made up by the news teams. So can we have a talk on that? And I asked around and eventually was told, well, you can't get anybody better than Chris Rodell because it's just what he's working on right now. So I'm very pleased that Chris has taken time out from his working on his thesis to tell us about this recent heat wave and the science behind that. So Chris, it's all yours.
Thank you very much, Dr. Scott. All right, so I'm going to go ahead and share the screen. Just holler if you guys are unable to see anything. So yeah, thank you all. My name is Christopher Rodell. I'm a PhD student in the Earth, Oceans, and Atmospheric Sciences Department at University of British Columbia. I'm advised by Dr. Roland Stoll. We're in a kind of subgroup called the Weather Forecast Research Team. So today I want to kind of discuss that heat wave that we experienced in late June and early July. Kind of give you a breakdown on what caused it, and yeah, some of the factors that played into making it so dang warm in our area. So let's see, there we go, I got the controls. All right, so things we're gonna highlight today. So yeah, we're gonna go over the heat wave. We're gonna touch on the headlines because there were a ton of them, and there were a lot of them for very good reason, because this thing was unprecedented. It broke endless amount of records. I'll touch on some of the timing and locations of the event and share some of the fun records that were shattered throughout this period. So for part two, we're going to kind of break down the setup and what led to the event itself. I'll talk on how La Nina was a bit of a contributing factor and go into the upper air dynamics of kind of what set the stage kind of on the Eastern Pacific side of the world before it made its way over here. And then we'll talk on something called a thermal low, which was a really big player within this event, and also the topography and how it altered kind of the heat component of everything. Next, we'll go into the aftermath, talk about kind of the wildfires that arose after the fact, and the intense flooding due to rapid snowmelt and glacial melt, and touch on some of the human component, such as the poor air quality that was created, and also just the heat impacts that humans experience in these kind of events. So let's see, there we go. All right, so the headlines, like I said, this thing just absolutely shattered records. We had, numerous records, daily records being broken for multiple consecutive days. There were an immense amount of aquatic life that was killed as a result of this, just from the intense heating. It was just incredible event, well covered, and as your colleague alluded to, it may have led to some confusion. Specifically, the media really latched onto that heat dome term, and it may not have been overly clear. We'll actually talk about that in a little bit, and hopefully, I can provide some clarity as to what a heat dome is. And a bit more scientific standpoint. So timing and location, hopefully, I'm sure you guys all know, it occurred in the western portion of North America. And so you can see here, this blob represents a 2-meter temperature anomaly in degrees C over the 3-day period when it peaked over British Columbia between June 21st and June 29th. And you can look at this map and see that temperature anomalies were upwards of like 19, 18 degrees C in some locations, which is just like absolutely unbelievable. Also want to note the remarkability of the time of year that it occurred. It happened in like late June, which is very unusual because typically our hottest time of the year is in August after, the solstice has occurred, more, the waters have warmed up, the land surface has warmed up, and that's typically when we experience the hottest times of the year in North America. Also, it happened post La Nina, which played a big factor into all this. Just keep that in mind. So some of the records. Looking at the figure here on the right shows the June 27th observations, the maximum temperatures recorded at weather stations across the Cascadia region. So we've got Vancouver is kind of positioned here, Vancouver Island, we've got the Olympic Mountains, Seattle down here, just to orient yourself. It's kind of a lot on this plot, but you can see that most of the temperature anomalies relative to normal this time of year were upwards of 16 to 20 degrees C above normal. Canada broke its temperature record for 3 consecutive days in the town of Lytton, BC. For context, that's hotter than the hottest temperature ever recorded in Las Vegas at 47.2 degrees C, and also 10 degrees higher than Lytton's recorded temperatures before this year. Note, Lytton wasn't the only location to break the Canada all-time record. There were multiple cities. Lytton just happened to have the highest temperature of them all. Other records that were broken. So even compared to record high temperatures outside of this time of the year, it was still exceeding those records by upwards of 5 degrees C. So typically a heat wave would impact us in August, and the highest temperatures experienced during those periods were actually even broken. BC alone had 43 all-time records set for temperature. BC Hydro, our power provider, broke its summertime electric load for 3 consecutive days, peaking at 250 megawatts of power, or 2,500 megawatts of power. Looking at some local stuff at UBC, we have a rooftop weather station on top of the EOAS building. If you're interested, we actually have point forecasts at the locations. Here's the URL link if you'd like to check it out. But you can see the heat record, or the heat wave occurred during this period, and we also broke our climatologic records that dates back to 2007, peaking at about 36.5 degrees on June 28th. All right, so now that you guys know it was very hot during that period and you know where it was happening, let's look at what led to it. And first starting to delve into La Niña. Actually, I lied to you. We're gonna first break down some meteorologic jargon before we get into the talk. I realize some of you may not have this background, so it's important that we actually kind of define some key terms or things I'll probably be saying just out of just habit. So first, we're going to define something called synoptic scale meteorology. When I say synoptic, I mean large scale, or like cyclonic scale meteorology. You can think of these things of horizontal length scale on the order of magnitude of about 1,000 kilometers. So if you look here, these are kind of upper air maps, and you're looking at large features that span across most of the continent. Another key parameter I want to define is something called geopotential height. Geopotential height is a really useful metric for atmospheric scientists to monitor. Basically, what it represents is the height approximate actual to the height of a pressure surface above mean sea level. And so typically we like to look at these different pressure maps. So say here we're looking at the 200 hectopascal map. On average, it sits around 1,200 meters above ground level. And then what we can do is look at the geopotential height lines on that pressure surface, and we kind of form what were called iso height lines or contour lines. And these lines are drawn on these constant pressure charts, and they represent altitude at which a particular pressure occurred. And these are, lines of equal height, and they're kind of analogous to topographic charts. And so in essence, we're basically painting the atmosphere in a 3-dimensional field, kind of like you would a mountain map, so topography in that regard. Other things to note, so we actually look at these different layers that represent different heights. Pressure obviously is decreasing at height because there's just less air above you to exert force down. All things that are pretty clear for, I'm sure, you physicists. So other key meteorologic jargon are the troughs and ridges. So these are important. So say we're looking at something like the 38 kilopascal or 300 hectopascal heights. And these are, around about 9,000 meters above the surface of the Earth. These are a good height to actually represent the jet stream. And so what we like to do when we look at these heights, we plot these contours, and then we can tell the height differential across them. This height differential then be able to kind of dictate where areas of cold air and warm air are located. And so typically under a trough, which we see here, which is oriented from north to south, we typically have a zone of cold air. And then under a ridge, which would be kind of just to the east of this typically, is an area of warm air. And why this happens is that as air is moving across, it gets slowed down as it's coming through a trough region, and then it's accelerating out of it. And this creates a divergence aloft of like kind of the upper portions of our troposphere. And this divergence then kind of creates a void that gets filled by air underneath it. And this air gets forced to rise. And this creates a lower pressure surface at a lower pressure at the surface of the Earth. And then this ends up getting circulated due to Coriolis effect. And this kind of circulates cold air from the northern latitudes downward to the pole. It brings down cold air from the poles down equatorially, and then it brings warm air from the equator kind of northward towards the poles. It's kind of like our Earth's like a equilibrium mechanism. It's trying to find balance. So this is kind of how it works. But the key thing is these troughs and ridges where they're located within all that. Another thing I'll probably say quite a lot is just anomaly. And when I'm saying anomaly, I'm always referring to the variations relative to the climatologic norm. And so say we're looking at geopotential heights, I'm referring to what that deviation is in the geopotential height based off the climatologic means over the past 30 years. And so moving forward, we're first going to look at this La Nina setup. What we have here on the left are sea surface temperature anomalies. So again, these are the temperature deviations based off the climatologic means over the past 30 years. And you can see during a La Nina event, we typically have colder air accumulating on the Eastern Pacific Ocean. And then we get warmer air accumulating on the Western Pacific Ocean. And this creates varying weather patterns because typically the warmer oceans heat the air through convection and create a lot more thunderstorm activity in these locations. And then on the converse side, this colder air is typically suppressing convection. And this promotes a little bit of waviness within the actual jet stream. Other thing that it also does is it kind of piles up a lot of heat energy in certain locations. And so when you're looking at source regions for warm air, it can pull from certain locations, such as this area, which happened to occur during this heat wave event. But we'll get into that in a little bit more detail. I guess I should have also defined the plot on the right is just the sea surface temperatures that were being observed during this period on Monday, June 21st of this year. So moving forward, we're going to look at some of the upper air dynamics. The plot on the left represents 85 hectopascal temperature anomalies. 85 hectopascal, just to orient ourselves again, is about 1,100 meters above ground level. And so we're looking at the temperatures at that fixed pressure plane. Also, we're looking at the 500 hectopascal geopotential heights in decameters and their anomalies in meters. And so that puts us at around 5,600 meters above ground level. And then the actual geopotential heights are represented by the black contour lines. And then the coloring underneath is represented by the anomaly in meters, which is kind of shown here on this bar. And so what you're seeing is under a trough that I've labeled here, you're seeing colder air associated with that at lower levels in the atmosphere. And conversely, at the ridge, you're seeing hotter air under those areas. And that's just because hot air expands, causes it to rise, lowers the pressure, etc. Anyway, so what we're going to do now, we've kind of oriented ourselves knowing where troughs and ridges were located on this map. We're going to kind of animate through time and look at the evolution of this a few days prior to the event. If you recall, it peaked in BC around June 27th through June 29th. And so we're looking back at Tuesday, the 22nd of June. And you can see this very powerful trough that's kind of digging in. And when I mean digging in or deepening, is exactly what it sounds like. The surface level of the 500 geopotential height is actually sinking down vertically. And so when we move through time, it actually creates this very deep layer and this tight pressure gradient across. And it's driving a lot of winds and bringing up hot air from this warm zone that we saw on the oceans, kind of pulling it into this ridge that's located here just east of this trough. And if we move forward a little bit, this is at its deepest stage when it's really starting to pull a lot of this warm tropical air up from north of Hawaii up into this ridge and just starting to accumulate it. And then we've got these two other low pressure systems kind of sitting here. And this is kind of not allowing any of this air to kind of push further east. And so it's just kind of getting spun around clockwise within this ridge. I kind of overlaid the sea surface temperature plots just to kind of give you an indication of the source region of most of this air. So if you follow these lines, winds are moving parallel with them at this height level, and it's driving a lot of this warm tropical air up and towards it and trapping it into this ridge here on the east. Advancing forward, we see that this ridge is beginning to rise and the trough is kind of starting to fade out. As the ridge rises, we start to see temperatures really start to build over British Columbia. And as we move forward in time, it continues to heat up. Now that we're into the 28th, this is the day that the day prior Lytton broke its record. And then the 29th is really when the event peaked. And then it starts to make its way east. So what we're going to do now is we're going to look at the same field, but we're going to shift to a different domain. And so instead of centered over the Pacific, now we're centered over North America. We have our trough and our ridge again. We're looking at a period in the 24th of June. So this is when the trough was its deepest, pulling all of that hot air from the equatorial Pacific and starting to build this ridge or this potential heat dome that we hear so much in the news media. we're going to move through time, and you're going to start to see something that, it's commonly referred to as an omega block. This is the ridge that kind of gets formed. It looks like, the Greek letter omega, and you've got a low pressure system sitting off to the east into the west, or east into the west, and this kind of doesn't allow it to actually move. And so any air that is within that is just kind of sitting there. And as the air is kind of accumulating, it's actually building pressure and causing air to sink. And subsidence allows, or doesn't allow clouds to form. And so this promotes all the incoming solar radiation to actually hit the Earth's surface and cause even more warming. It's like this positive feedback that occurs. And if we continue forward, this is kind of a great graphic that actually represents this heat dome that we hear so much in the news media. And so on the left, we see the 500 hectopascal geopotential height and anomalies during the peak period of the heat dome formation in the omega block. And what happened was, we saw it before. So in step one, there'd be a warm Pacific air kind of gets trapped up into the jet stream. We illustrated why that occurred due to the trough just north of Hawaii and pulling all that air up. This air, starts to warm and expand, rises upward, and the high pressure forms, and then it prevents any warmer air from escaping. And so as this pressure is building, the air is subsiding and denying any cloud formations to occur. And it warms, kind of comes to the edges and recirculates around, such as that. And so what's happening is the ground is losing moisture, and wildfire behavior is actually increasing as it dries out the forest fuels. So another really important component of all this is kind of stepping down in the atmosphere. We're analyzing at 925 hectopascal, so about 780 meters above ground level. So we're sandwiched between these two layers within the atmosphere. And there's a phenomenon that occurs, something that's called a heat low. And they typically are sourced in desert regions where the land surface gets extremely warm and it causes the air to rise around it. This actually lowers pressure relative to the areas around it, because hotter air is less dense than warmer air, and it kind of creates this low pressure just at the surface. And to illustrate what that looks like, if the ground level was heating up quite a lot, it actually is rising the air and causing these pressure heights to decrease under a stable atmosphere at 500 hectopascal. And so this is exactly what occurred kind of here down in the Death Valley area, and formed what's called like a thermal trough or a heat low. And this low is forming kind of on the eastern or western side of the Cascade Mountains and coastal range of North America. And so this low pressure system formed and started making its way north. We're now onto 0 Zulu on Monday on the 28th. And this low pressure system kind of started making its way north up the coast. And you'll notice that the high pressure system sitting here, and typically pressure, goes from high to low. And so it's driving air across the mountain terrain. And it's promoting this very tight gradient that forms across the mountains, and it's causing all this descending air across the mountain range. And this is a really important thing, which I'll highlight here in a second. This low continues to kind of form, ends up kind of killing itself off by circulating colder air within it. And then, it eventually kind of fades away. But so I wanted to go back into the topography and talk about how that played in with the positioning of that heat low we just saw. And so if you're not too familiar with the area, we had the Cascade Range kind of south of us that runs up from Oregon into Washington. Then we've got the coastal range here that runs, you guys are familiar with the coastal range, and then also the Rocky Mountain Range. Vancouver is positioned here where this red dot is. My cursor is kind of highlighting the location of that. And now we're looking at the temperatures at 2 meters above ground level, and also the sea level pressures in hectopascal and vectors at 10 meters. I want to kind of drive home the point that you're going to see that winds are going to be moving from the high to the low, and they're going across the mountain range and getting forced to descend. And as air gets descend, it's getting, forced, more pressure is being applied, and it's actually causing it to warm up quite a lot. And so we see just that as we move forward. We're getting now into kind of the hottest period of the day, 0 Zulu, 6 hours off. So that's about 5 p.m. local time for us. And we're getting upwards of temperatures into along the coast in the high 30s, which is absolutely unbelievable for this location. And so it was the positioning of this low coming in, plus with the ridge forming and kind of building up this warm air, and then the low forcing it to go down the mountains that really just turned the heater on over our location. Okay, so now that we kind of understand the dynamics at play and why it was so warm over our region, let's look at what this had done to the environment. So this graphic represents fire danger rating, where it's a system used by the Canadian wildfire agencies. It's called the Fire Weather Index system, and it's a numeric rating where higher values represent drier conditions. So what the forest experienced through this period were these really warm conditions that heated up the forest vegetation and evaporated a lot of the moisture out of it. And this causes the moisture then, or the vegetation, to become more susceptible to fire. So if a fire were to occur, it's going to burn at a higher danger or higher severity. And you can see just over the 6-day period from Wednesday the 23rd to Thursday the 29th, there was very little fire danger within British Columbia, Alberta, Saskatchewan. After the heat wave, the fire danger was absolutely unbelievable, kind of, heading upwards in the highest portions of these charts. And what happened next was we had, unfortunately, a couple human-caused events. And so fire, obviously, it needs an ignition source to start. And during that period, there was no lightning. There was nothing that could have started it, but there were humans. And humans kicked off a couple fires. The two of note, so what we're looking at here is, this is in British Columbia. I'm going to just pause it and back up, actually. And so what we have here, this is Kamloops Lake, and this is the town of Kamloops. This was the fire just north of the McKay fire. Here is the Lytton fire down here by the town of Lytton. And then this fire, the name escapes me. But these were human-caused events. And what happened was they started in very severe fire conditions. Because after the heat wave, there was a bit of an unstable layer that came through and promoted kind of positive buoyancy throughout. And this kicked off an event called a Pyrocumulonimbus Cloud, where a thunderstorm basically forms over a fire. Unfortunately, the thunderstorm didn't actually produce much precipitation, but a ton of lightning. This system, the main one here, produced over 27,000 lightning strikes just within the overnight period. And this ignited another 40 fires just downwind of the event. And once it kind of gets rolling like that, it's pretty hard for fire crews to get to a quick response and suppress all these fires when there's just that much activity in such a short period of time. What this looked like, just forecasting the smoke, you can see, again, this is the same period we looked at with the fire danger, but extending a little bit further out into the future post-event. BC actually had very little fire activity, as did Alberta and Saskatchewan. Only a handful of scattered fires throughout the area. Afterwards, there were on the order of a couple hundred fires that were ignited, all as a result of this heat wave. And it's causing an immense amount of issues. The fire season started much earlier than normal. And unfortunately, we're only rolling into our hottest months of August, where fire activity is going to be continuing to increase. And so we might be breaking records for the most area burned this season. We're certainly on track for it. Other big implications of the event were the loss of snowpack and glacial melt. I also wanted to note too, it is pretty remarkable that the heat was able to get so hot the land surface because there was actually more snowpack across. And so you would think, higher snowpack, higher albedo, it would be reflecting more of the incoming solar radiation out. But even then, just because of how the conditions were, it wasn't enough to kind of suppress how much heat was coming down. And this caused rapid glacial and snow melt. This is two images from Sentinel-2 captured over the Saskatchewan Glacier in Alberta. And you can just see the amount of snow and ice that was lost just over a very short period of time. This is also over the Sutfield's Peak in Alberta, pretty close to the Saskatchewan Glacier. And again, just so much snow and liquid or frozen water was lost as a result of this event. And what we saw within the rivers, because of the rapid snowmelt, was unprecedented discharge rates. This is a graph showing the discharge rates from the river just outside of Baker on the North Fork Noosak River. This was an increase in discharge 40%. It exceeded the average increase due to similar heat wave events by over 23%. And it was likely due to not just due to the severity of the event, but the timing of the event, because it probably happened so much earlier, there was just more available snow to actually melt to increase this discharge. But this also plays big implications, particularly in places like British Columbia, where all of our electricity is reliant on, hydropower. And it's a challenge for folks in those types of agencies to not, moderate how reservoirs should be kept, because we lost so much. The mountains act as a natural reservoir, but you can't, the reservoir can only be so filled, so perhaps they had to let some out and just keep it at a certain level. So we may have actually lost some useful energy in the future. It's kind of hard to gauge that at this time. Another really big impactful thing of this is the air quality. You guys may have noticed if you were outside just how bad the air became as a result of the heat wave. The heat dome itself, as we illustrated, is trapping this air and it's not really having an opportunity to mix out. But as emissions from vehicles and stationary sources are trapped, they get irradiated by sunlight. And this leads to the formation of a host of pollutants, including ground level ozone, or O3. And we're unfortunately having to breathe this in, and we have to kind of just deal with the consequences of it just due to the current way we like to move around and produce energy. Other big human factors of this. So as I mentioned, the air came from the equatorial Pacific. So it had a pretty high amount of moisture content stored within it. And even at high temperatures, the relative humidity values were still fairly high in comparison to normally what you experience in like a desert area, Las Vegas, for example. There were still RH values on, upwards of 50. And this is a problem for humans because what we do to cool ourselves is we sweat. And sweat, forms on our body, it evaporates, and then due to latent heat energy, it actually cools the area just above our skin. Unfortunately, when it's hot and humid, you don't have that cooling capability because the sweat isn't as evaporating as quickly. And so it makes it very dangerous for humans. Current estimates were that there was an increase of about 195% of sudden deaths. This will probably be more information will definitely be coming out as more people study this stuff. But it's very important that we actually gain better understanding so we could provide more early warning to these systems, and so that folks can take the proper precautions so we can eliminate any of these unnecessary deaths that may have occurred. So yeah, I guess that really kind of captures all of the talk. Hopefully I didn't go incredibly fast. I did. So I'll just kind of recap. We discussed the heat wave. We went over the headlines. Told you about the timing and location. It really peaked over BC between the 27th and the 29th of June. It shattered multiple records. BC hit 53 daily high records, broke 43 or 42 all-time records. In Lytton, BC, broke the Canadian record high temperature for 3 consecutive days. I showed how La Niña played a big impact in this, as providing this really warm source air, warmed the atmosphere a lot just due to the sea surface temperature patterns, and provided this warm source air to get trapped up into this omega block or ridge, where we looked at the dynamics. And then we also talked about the thermal low and the positioning of it in relation to the topography and how it promoted a bunch of downsloping winds that caused more heating as a result of the downsloping and pressure increase. Also showed you the aftermath of the wildfires and how much wildfire activity increased in the environmental impacts from the flooding and the poor air quality, and what it had impacted on humans. Let's see. So yeah, I guess that concludes the talk. I really appreciate you guys all joining us today. And I've opened the floor for questions. Thank you.
Yeah, great. Let's thank Chris